Hey everyone, welcome back to Neural and Wires. So today we're covering something super important for deep learning models, which is a layer normalization. So guys, why should we care? Because if you ever train a neural network and it failed it failed to converge, normalization might be the missing piece. This technique stabilizes training, improves learning efficiency, and helps deep models work better. Transformers, including GPT models, heavily depend on layer normalization to process information smoothly. By the end of this video, you'll fully understand how layer normalization works from scratch and why it's better than traditional methods like batch normalization. So let's jump right in. What is normalization? Before diving into layer normalization, let's quickly understand normalization. So why do we normalize? Imagine you're training a model and your input data has numbers ranging from -1,000 to +1,000. This can create huge variations, making training unstable. So we bring everything into a standard range. So traditional normalization works like this. For example, so this scales the data to have a mean 0 and a standard deviation 1. But here's the problem. So why don't we use batch normalization? Because batch normalization was the original fix for unstable training, but it has some problems. So the problems with batch norm is it needs large batch sizes to work well. It computes statistics across the entire batch and not ideal for RNNs or transformers. So layer norm is better because it works even with small batches or single inputs. It computes statistics within each individual data point and is perfect for transformers. So a key takeaway is layer normalization is better when we are dealing with sequential models or when we have small batches. So let's understand layer normalization in code. Let's walk through the actual implementation of layer normalization from scratch. So guys, this is our code. So self apps. So this is a small value to prevent division by 0. So this is a learnable scaling factor, and this is a learnable shift factor. And so this one, let's we compute mean and variance for each data point, not across the batch. So this one mean along feature dimension, and this one variance along feature dimension. And so this one this normalize the unit normalize the input data, and this one this scale and shift using learnable parameters. And let's break this one down. So we compute the mean and variance for each input data point. This ensures that every input gets scaled individually instead of using batch-wide statistics. So we normalize the input by subtracting the mean and dividing by the standard deviation with a small EPS to prevent errors. We apply two learnable parameters, gamma, a scaling factor that controls the range of values after normalization, and beta is a shifting factor that reintroduces a learned bias to the data. These parameters allow the model to undo normalization if needed. So guys, step 4, we test the layer normalization. Now let's create some random data and apply layer normalization. So this is a 100 dimensional input, 32 data points, each with 100 features. And we apply layer normalization and we check the output shape. So this is our output. So that's actually great. This shape is preserved, meaning layer normalization processed each data point correctly. So step 5, let's check the mean and variance. Let's check if layer normalization really worked by printing the mean and standard deviation. So The output is, this tells us that each feature across all samples is roughly standardized, and so mean and standard deviation of a single output, so tensor, so this is actually perfect because this means is it is very close to zero, and the standard deviation is almost exactly 1, which is exactly what layer normalization is supposed to do. So guys, why this matters for transformers? Because most modern AI models, including GPT, replace batch normalization with layer normalization because it doesn't depend on batch size, and making it perfect for sequential data. It ensures stable training even for very deep networks. And it allows the model to adjust using learnable parameters, which is a gamma and beta. So final recap is, so what we learned today is, we learned why normalization is important that in deep learning, and why layer normalization is better than batch normalization. So how layer normalization is implemented from scratch, and why transformers and GPT rely on layer normalization. So guys, if you found this helpful, make sure to like and subscribe to Neural and Wires, and comment below. So guys, have you ever run into a unstable AI training, and what helped to fix it? So in the next video, it will be exploring how multi-head attention works and why it is so powerful. And we'll be wrapping up everything. So guys, don't miss it. So all right.